on the regarding the agenda, again, we're pretty good about putting all the links in the chat, but if you do want to be here under home, there is that workshop agenda. It's also in the linked in the chat. So in any case, here we are though. We'll situate the course within, do that whole year overview, the 30,000 foot view, then dive into kind of an overview of the whole unit on texting and driving. And then really we just get to, the 10,000 foot level and look a little more closely. Chance for a breakout room in the middle and a breakout room at the end. And importantly, we really do need, really hope you can do those exit tickets. We'll try to finish on time, so it's right in that 2 hours. Again, just the accountability of public funding. We want to show that money is well spent. Okay, so situating the course within the NGSS. I'm going to just show it under home. This is just something occasionally you want to check in on. Timeline for the sequence. And so here, here's kind of a visual image of the whole year. We did the patterns unit. A lot of people are probably in that right now, getting those anchoring experiences. Sometimes people always like to hear where other people are, and sometimes that puts pressure. So no pressure, but people always just ask. So we're doing the packing tomatoes quadratic lab myself. Texting and driving is the one we're talking about. So you can see we're going to have a proportional horizontal line, quadratic, and actually a couple of proportionals and a couple horizontal lines and a quadratic. So that's really nice. Just to say it, because people haven't heard it for a while. There's a bungee jump with the energy and engineering. And then unit 4 is engineering a shoe. Really good one. That one does bring up that inversely proportional a couple times there. Okay. And then what's happening, how do cell phones work? And then electricity, power production, and climate science. That's electric guitars and climate change. So you'll hear us make a reference of how to save some time today and space in the universe. All right, but as we can see, we got performance expectation, and we've been meeting with an NGSS writer, and she is constantly reminding us the performance expectations are for 11th, maybe even technically 12th grade, but most states only require 3 years of science, so students need to get there by 11th grade. And so lots of students are not ready for a performance expectation too early in the year, especially one that's at the 11th grade level. So you can see we start with just one in this unit, but it does increase unit by unit. And just because it's right here, let's also quick look. There is 3 sort of major opportunities for assessment. The constant acceleration lab, the big ideas of acceleration, and the culminating claim evidence reasoning, the scientific argument around texting and driving. Okay, so there's that peak. I might even close this now. Yep. There's the idea capture tool. I have it open on another slide, so I'm gonna close that for now just because I usually have so many tabs open. There's that Oregon sign-in sheet, so you can sign in right there. Okay, and then we are at the unit overview, and I'll throw it over to Matt to just give us an overview.
Good. Yeah, thank you. So I wanted to give a just an overview of just take a 10,000 foot view before we start diving in and looking at the individual tasks that are there. So again, that performance expectation is all about designing a solution to a complex real world problem by breaking it down into smaller parts. And we really strongly emphasize system analysis, breaking that down into smaller parts, and then using that as using that system analysis as a map of where we are going to go next. So this is also around how do we use STEM to enhance the social discussion. So as if you're familiar with the teacher calendars, we have the tasks there, and if you don't mind scrolling down, tasks and activities for each different section, and just a recommendation for time spent. And with that, we have all of the big links, all of the keys and helpful files that you might find within that document. Helpful videos, things like that. There's also task narratives there that are available to read and before a task to look at the goal for that. From the big picture, students are given a real world challenge in this unit around texting and driving, which we'll get into. They're going to break it down into smaller pieces and find models and do some computational thinking. Ultimately, the goal by the end of the project is that students are going to argue from evidence of how dangerous the texting and driving scenario is using our claim evidence reasoning format. So with that, we will jump in and dive into some of the smaller pieces there that we see along the way.
Nice. And in our model, we always start simple, build to complexity. And you'll see how much, like, it's really nice. This unit shows like 2 or 3 different levels that we do that on. So, just if I know actually some people are already here and have done it. It's always a fun one. So just think, and it doesn't have to be a pizza if you want to change it to something else. But yep, if you were to order a pizza, and I was going to say on the phone, and students always correct me, no one uses a phone to order anything. So it's an app or something like that. But fine, you hit on your app, order a pizza. What are all the things that have to happen? You got to make the pizza. You got to get out the tomato sauce. And, students are all over the place. Lots of times when I'll keep it short. All right. So ordering that pizza, and I don't want to go over this too much detail. Okay. So it's just some fun highlights here is they come up with 10 to 15 things, how you got to drive it, all that good stuff. And then just as a simple one, get it now, chunk it. Can you get it to 3 big things that you need to have happen when you order a pizza? And you can see some fun ones down below, and we keep adding as you got good ones. Please do share it. So the most common one is make it, bake it, take it. Yes, nice. That captures it. Make it, bake it, take it. Put together your pie, turn the oven up high, get in your car and fly. That's awesome. It's just enjoyable to pull kids in. Different kids get excited. Sometimes they come back a day later and they've come up with another good one. Stress, mess, success. Call, cook, carry. We keep adding these. So yeah. So in any case, that's that idea. Take a big complex problem, making the pizza and getting it there, break it down into simpler, more manageable parts. And ultimately, what I want to say is this is a very student friendly. It's low stakes. It's not intimidating. Students have a chance to contribute and get talking. There's a lot of talk structures if you want to add even more structure to it here, but that's really a setup. This doesn't want to get this whole thing is 10 minutes, and that really sets us up for texting and driving. But I do want to, we've gotten enough questions that we did iterate this letter to make it super clear. So ideally, the best thing to do is to talk to your health teacher. And I mean, really do this if it works in your school setting. Talk to the health teachers. Every health class in high school, they will talk about texting and driving during some unit. I think it's called Wise Choices. And I don't know if that's just a district level or state level, but there's like a unit where they talk about healthy decision making. In any case, if you can get your health teacher to really use the spreadsheet in class, that is awesome. And that's truly authentic. So that's the ideal goal. That might be too much. If you can just get your health teacher to ask, and it depends on how much you want to play into this, but you could have a health teacher come and send a student down. And sometimes the students forget what to say, but it's all good. Otherwise, the simplest thing is to have your health teacher send you an email, and that way you're not dependent, but it just depends how much you want to do it. So here is a a sample email that we ask our health teachers to send us. And then we actually just pull up our email and show the students. So, hey, we're studying the risks of texting and driving in health class and need to better understand how far a car goes during texting and driving incident. And then this next sentence is really important. We want to quickly figure out different situations, like different speeds, time of distraction, and see how far the car travels, right? Because it could be in a parking lot, it could be in a neighborhood, it could be on the freeway. All right, could you code a spreadsheet for this, right? Could you code a spreadsheet for this is probably not something the health teacher would naturally say, but if, you think that students just need that to be able to, sorry about that, need that specificity, that'll guide them. If you want to just leave it more open-ended, here's one that's a little more typical of what a teacher might write, but then that's a little bit with you working with students to figure out, hey, how could we do this? Spreadsheets are really nice. You can put in the number, it'll auto calculate, do all that computational thinking and get you answers quickly. But if that might be a stretch for the students and it just turns into you telling them, it's a little bit nicer, more authentic to have that come right in the email. And literally we just have the health teacher send this text right back to us. So it can be that simple. And we've done it for enough years now that, if you do this for enough years, there's 11th graders that had a student come back to their 9th grade class and they asked the health teacher to be the one to go do that. So anyways, it's fun to do it with students, but this email works really well.
Mr. Hill, may I ask a question?
Yeah, we do prefer the most questions to be in the chat or the idea capture tool for the flow of the webinar.
Okay, got it.
Yep. Great, thank you. Okay, well, yes, so that's just that peek at how to launch the unit, and that student or the email would come up right after that pizza activity. And of course, now you're going to do the same thing with texting and driving. All right, with that, I'm going to close this and hand it over to Matt for the next step.
Yeah, so once we get the email from the health teacher or have a junior come into class and ask what we need, we really want to start by defining a problem. And this is where we introduce the packet and the engineering problem statement that goes along with that. So right in the top of the packet, we want them to start by getting a handle on what they're doing. So Bradford, if you click on the next slide, we saw, don't have it there. Yeah, so we're looking at, we as app developers are trying to predict how far a car will travel while involved in texting and driving incident for our health class. And that allows the students to get a handle on, like, what are we actually trying to do as in this unit? What are we doing as our goal? And then that allows us to start to break the problem down into smaller, more manageable parts. So one of those pieces is linked to tools for solving complex problems. We want to do that. So we're going to show you the video that we show in class, and this has lots of that. Just get some brainstorming of what kinds of situations and things do we need to think about to do that. So yeah, Bradford, if you don't mind showing that. I don't know if you'll need to stop and reshare for those.
Oh yeah, I probably should. Yeah. Excellent. And we'll see that there's 4 different versions of the video, and you might use each of them at different times. Excellent. I'll do a quick overview and then I'll hand it right back to Matt. Here is the long version, which we only show one time. Long version with no graphics. long version with graphics. Actually, the students made this one. We don't really use this one either, because after you show the long version, no graphics, then we pretty much, when you re-show it the second, third, fourth time, we just use the short version, no graphics, until they come up with, they read out the information from the video that they need. And once they've kind of discovered it, just it's helpful to have those visuals, or this is a support if students are struggling to come up with what key information they would need. You could show this one. Okay, with that, I think we'll show the long version one time and then maybe even watch the short version. All right, I think we're ready. I'll get it started and go into full screen.
Hey, it's Julian. Yeah, I don't know where he is.
I'm on my way.
I'm gonna be a little late. Chris isn't here yet. I've texted him a few times, but he doesn't seem to be responding. Oh,
I just realized, and we actually want to have you consider doing this with your own students. So this does depict in a made up scenario, it does depict a car showing a pedestrian being hit. There's nothing graphic here, but it does show that there is, well, it's graphic in the sense that the student is lying on the pavement here. Something that just we know that this lands with a lot of students because they've been in cars with texting and driving. And there have been students, I've had students myself who have been in a texting and driving car accident. It was car in car, not car in person, but and they actually every student's different. I don't want to categorically say, but they were glad that we had this unit, and it wasn't like awful for them. They actually did appreciate this unit. So, but that can be different depending on different people's experience. So we just do have this question, what will happen? And it'll just show the two possible outcomes. So just be ready for that.
I'm on my way.
oh, there you are.
Good. And just to show, if you go up one slide, just to show, there are, you may have, if you're familiar with the materials, there are slides in there that have this, and that was just a note there for you as you're preparing for teaching your students. So after that, we do look at, want to start to look at the situation and think about how do we break it down into smaller parts. So if you click on slide 17 for me. So we've watched and rewatched that texting and driving scenario, and we want to really be explicit about giving students opportunities to, think through, draw, model, and look at the scenario. So in this case, our students have either butcher paper and markers or whiteboards, and we want them to model using pictures and words the scenario that we just considered, the texting and driving scenario. In a similar way to the warm-up, which was with the pizza, the pizza activity where they were breaking the pizza being delivered into smaller parts. Similar here, from the moment the distraction happens to the moment the car comes to a stop. Then if you go to that next slide, please. Then we want them to start to chunk those into those 3 big groups. Earlier, Bradford mentioned, make it, bake it, take it is a popular one for the pizza. Well, this one might be what distraction, reaction, and traction was a big one that they come up with, or time of distraction, time of reaction, and then the braking part. So we want them to start to take that bigger piece and break that down into those smaller parts as they're going. And then, if you don't mind going to that next slide, Bradford. Then we want them to start to identify like what variables might affect the end result. So highlighting using red marker, what are those different variables that might affect the ultimate outcome of this? And of course, those things that affect the ultimate outcome of the scenario are things that we want to consider in our final spreadsheet app that will be doing that prediction. Then finally, Bradford, go to that next slide for me. Finally, we want them to walk around and see what other groups are doing. So they're going to walk around, find how other groups illustrated those things and identify those variables. And lastly, they really want to go and take back what they learned using blue marker, iterate on their own model as they're going forward. Bradford, I'll hand it off to you for step 7 and 8.
Nice. One thing we didn't show on the packet, right after they get that, either that student comes from health class or you have that email, we try to get in one sentence right on the front of the packet so that they see it every day, right? So what are we working on? Oh, we got to create a spreadsheet to quickly figure out the distances involved in texting and driving. So it's right there. And there's slides that support you in doing that. Okay, so we used to start with a blank sheet of paper, and that at times just took a lot of time, and it was time that was not necessarily thinking time. It wasn't high level thinking. So this is actually support level 2, which is a suggestion. In year 1, if you feel like it's the right fit, I closed the packet, which I'm sad I did. I'll just flash up in the packet. There is that brainstorming page that they can do on their own, and then they do that stuff as a group. And then here's the system analysis. So you can just see that's a pretty basic graphic organizer. They're just boxes, but it's pretty suggestive. Here, if you think that's going to take too much time or it's not the right fit for your students, that you can have, level 1 has a little bit less than this. And then here we're looking at level 2. A lot of things are pre-filled. Now there's less ownership when it's more like this, but those resources are all there for you to decide what's the right fit for your classroom. So in any case, we did want to give you a peek at this in terms of they come up with almost all of this. So depending on which level you pick, almost every student comes up with the velocity of the car. Every student comes up with time of distraction, how far the car goes. And that's going to be what we kind of anchor on: the distraction, the reaction, braking, or traction. Traction rhymes, so a lot of times distraction, reaction, traction. And then the question is how far it goes in each of those. So here students come up with this, and actually we didn't have it open already, and I wish I did, to show you the end. Why are we being so particular about the order here? Because I want to actually, I'm going to throw this slight audible. Matt, do you want to walk through the rest of the bottom of the reaction and braking, and then I'll get the 2CT pulled up?
Yeah, so a big piece of this is engineers often start with like simpler diagrams and then start to get that model down in a more complex way. And so we really want to identify the key parameters that in the plan to have them figure out. So that's really what this is about, is like looking at the reaction period and seeing what are the key things that we want them to, that we need to know to figure out how far it goes. And then of course there are all of these other things that students bring up that we want to later on be able to modify our scenario to be able to handle. And so these in the system analysis, the partially completed system analysis has all of those very key parameters. And I think Bradford will show you with this is all done with intent, with the end in mind. So if you want to show.
Yeah, I'll go back and forth. And right before I leave to this, I'm zooming the wrong way. So at the end, we want students to really synthesize this. At first, they're caught up in the details. We want to start simple and build to complexity. So I almost want to ask you to put it in the chat. Just get this a little bit interactive. Like the speed of the car is going to depend. How long you're distracted. What are some other things that would affect whether the car hits the pedestrian? Yeah, thank you. Could we get a couple? Because I want to show, and we want to write all of these down. Age of tires, road conditions, weather. Yep, road conditions, driving environment. Yep, rain, ice. Excellent. Remember those. At the end of this webinar, we're going to circle back, and we want to do the same thing with students. Get that written. Lots of times you have that on a board, a poster paper that you leave up in the class. So we're going to say, start simple, build to complexity. So what's the simplest road conditions? Okay, the dry pavement. What's the simplest time of day? Okay, daylight. All right, but good. We will come back to night, road conditions, brake pads, all of those things. That's excellent. But just for continuity, because the webinar is sort of fast and furious, it all comes down to, and that's this little if statement. And actually, this one is totally teacher-led. I do want to claim that most of the above students will say. They'll say the velocity of car, how good the brakes are, all of that. That can come from students. They won't put it in this order, but that's why we want to, either you want to use support level 1, or as you're bringing this from students, you want to write it in this order: velocity, time, distance. Why? Because when we get to the final spreadsheet, we want the system analysis to be the guide. And there's video tutorials that will help students. And we just know that sometimes if some students put just time of distraction first and then velocity, they get confused. And so that's a little bit heavy-handed on the teacher side. This is all coming from students, but the teacher is going to be guiding them to do that order such that you really set students up for weeks in the future. That's how vertically articulated this is, that they will have a ton of support to go ahead and take that page and turn it into a coded spreadsheet. And truly, that's a simulation. They are developing a simulation where they get the equations to code it from experiments that they perform and find the mathematical model for. So it's super neat. It is just really a positive experience. Overwhelmingly is what we hear from teachers about their students. Okay. I'm just going to do a quick check if I said everything I needed to say there. Yep. Okay. Yes, I think that is pretty good. So one last piece, and then I'll hand it over to Matt for the mini experiments, is we really want them to understand this piece of paper. This is not like they blindly fill it out and never think about it again. This is our roadmap for the rest of the unit. And so to really have it function that way, we do an exercise called Stronger and Clearer. And that's just where students pair up. I lots of times do it in the hallway. Maybe depending on your classroom setup, you might be able to pull it off. But we have a seating arrangement at each desk. There's just 2 A's and 2 B's, or there's just 1, 2, 3, 4 at each desk. And they just line up across from each other and they explain their system analysis. It's not going to be very authentic, but if you're just wondering, like, what do they say? All right, I'm going to try to model that in 60 seconds. All right, we are studying, as you can see, here's my system analysis for a texting and driving incident. Texting and driving, there's a driver in a car being distracted, and then they start to react. They realize there's a danger and they slam on the brakes. In the end, though, to figure out what's going to happen, the outcome, it will depend how far the car goes in total compared to how far the walker is. If the car goes 80 feet, but the walker is 100 feet, they're safe. If the car goes 110 feet and the walker only is 100 feet away, they are going to hit that walker. We broke this down, how far the car would go, into 3 big distances. The distance they go while the driver is distracted, how far the car goes while they're reacting, and how far the car goes while they're braking. I could probably end there, but I got 20 seconds left. So, all right, how far it went with distracted depends on how fast the car is going and the time of distraction. Same thing for reaction. Braking is a little bit more complicated. It depends how good the brakes are to just figure out how far the car will go in total. But again, we add up those 3 distances to figure out the total distance the car go and compare it to how far the walker is. Stronger, clear. That's not going to be your students on round 1. Just want to let you know that one. So anyways, and then they just rotate, and we do that 3 times. And I just want to say it's a heavy lift. Students kind of go in every time like, oh, do we have to do this? And almost every time they leave actually feeling good. They're like, whoa, I actually did get better that 3rd time. So again, it's always a heavy lift to have students talk and explain things like that. And they oftentimes are reluctant round 1. And it does. We've had students that have been absent and they just listen the first time and then start to talk the second time. So there's a lot of stronger, clear is something we use. You can't overdo it. Any strength overplayed becomes a weakness. Students will not do stronger, clearer every week. So we try to reserve it to really key times where we want them to explain something and really come to understand it well. And why do all that? Because then it's the roadmap for the rest of the unit. So about to hand it off. So where should we start on a sheet of paper? We start at the top. And with that, I'll hand it over to Matt to start to walk us through the system analysis and see where that takes us in this unit.
Sorry, before you close it, could you zoom back in, Bradford?
Yes.
To it. So as Bradford said, let's use our system analysis to figure out what we're doing next. So let's talk velocity of the car. How do we figure that out? Well, that's found by the situation. In the specific texting and driving situation, it might be the speed limit in the parking lot. We can modify that and look at that in other ways. So we have the velocity of the car. Time of distraction, we need to do a mini experiment to figure that out. And in the meantime, let's also do our mini experiment for the time of reaction, because we can figure both of those out at the same time. And so what are we going to do? Students need to come up with those experiments and think of ways that they can, modify, create, and do their own experiment. We have done this multiple ways. We do have some resources that we want to show you, that we've vetted and want to show you, but also want to talk about opportunities for creativity for our students. So Bradford, if you could click on that that's to activity up at the top, linked there. To the right one.
Yeah, good. I'm going to try to close some of these ones now to get us out of there. Okay, yep. Close that. Good.
So, we want to find, we got to do a mini experiment. This is an optional digital resource that we have given to students. If you go down 2 slides, Bradford, please. There's some instructions. We break our room up into halves. Half of the groups will do time of distraction. Half of the groups will do time of reaction. And there's resources down below, links and simulations that students can use to come up with their data. And so in a pinch, if you need to find some resources, there are some there. We like to also open it up to our students because we found that sometimes providing these resources kind of shoehorns, makes them feel like they're shoehorned, that they have to use those specifically. So when we don't give all of the resources to them, we might have them on the side if they need them. They tend to come up with more creative solutions to the problem. So they do funny things like borrow my rolly chair and push and try to like take their shoe off so that they can use their foot reaction time, not their hand reaction time of stopping the timer. Just fun things like that, where they are using their creativity to find a reasonable time of distraction and a reasonable reaction time. Just as a teacher note, students will, maybe they'll look at a recent message that they got, and they'll look at the time of distraction, and they'll come up with some just ridiculously long time, 10 or 15 seconds, when they're reading their most recent text and then replying, I'm on my way. And so those are great conversations to have. Is that modeling in the real world? Is that using that? And really any number that they come up with will be a scary number in terms of the distance that the car is going to travel during that time of distraction. So it really opens a lot of student creativity and allows them to start to think about, all of those different pieces of the real world situation that they can model in our classroom. So with that, I'm going to hand it back to Bradford to talk about what's next, our swirl.
Excellent. Excellent. So, swirl are speak, write, interact, read, and listen. And it's the webinar format. And so, but you can imagine there was a lot of speaking students have been doing during this time, right? In fact, we just came off of one where they're sharing out what, I think of it as Mythbuster style. They just got to do something where they can justify why they think 3 seconds is a reasonable distraction time. And so Matt already took us through that. So speaking, there's a lot of speaking in that, what are the things that happen in a pizza, all that good stuff. Writing, they've been doing writing in that driving question board that we did at the beginning here with what they did. Interacting, there's a lot of that too. And listening to each other. So we haven't done a reading. So there is a suggested pre-read strategy, squeepers, just one that's, essentially pre-read, read, and post-read. I will just jump to the slide with the reading. And it's actually an excerpt of the Oregon Driver's Manual. So that's really nice. And there's a separate sheet for students to look at. This is just a slide with a screenshot of it. But again, straight from the Oregon Driver's Manual, it even has this little, football field with a graphic. And lots of students look at that. What is happening with the miles per hour versus the graphic? That's not the prize. Sorry, actually, I didn't really clue us into what is the prize. So let's go back. The system analysis is what drives our next steps. So with Matt, velocity of the car, we got it from the simulation. So we know it's 10. The mini experiments that we just talked about, we now know the typical distraction time, and we just use whatever students come up with. And then we already know from unit 1 that distance equals velocity times time in the constant velocity situation. All right, so they can figure that out. They got the right model, and reaction is the exact same way. It's worth saying here, the velocity of the car during the reaction phase is the same, right? They haven't hit the brakes yet. They're going the same speed. The reaction time, that was done by the other half. I have like 9 groups. So 4 does distraction, 5 do reaction, and they come up with that number. And again, we can just take velocity times time is the distance. All right, so what do we need to do next? The velocity of the car before braking. This is always a good conversation starter. At first, students kind of say, oh, that's going to be less. And if, talk about it, ultimately, it basically seems they haven't hit the brake yet. And This also is the same. So until you hit the brake, the car basically is going the same speed that whole time. And then, oh, it is worth maybe calling this out. This is the one line that students don't naturally bring up. We do need it for the spreadsheet because the computer needs to be told, if you want to find out the change in velocity, you got to know what you started and what you end at. So again, this is one that the teacher might need to just say. And it's pretty natural though. Okay. And then they always bring up braking. How good are the brakes? And we saw that in the chat too. How good are the brake pads? All right, excellent. So we need a starting number. We will start simple, build the complexity. What's the starting number? That is what generates the need to read. It's nice that that rhymed. Okay, so once they need to know how good are brakes, that's what this reading does. Also, just a fun fact to know that almost every image, if it is connected to something you would actually need to do, that's hyperlinked. So all the Desmos graphs are hyperlinked. This actually would pull up the reading right here for you. I didn't plan to open it, but it's right there. I just want to show you that. Okay, so they need to read this to figure out, I don't want to show too many screens, but I just want to say that one, oops, that's the key. So I didn't, oh man, I got myself all, we need to figure out what is the deceleration due to braking? How do students figure it out? They read the Oregon driver's manual, and it actually does ultimately say down there. So it turns out that the Oregon driver's manual assumes about -8 meters per second. So that is how they find that out. And they would go back and now enter in the -8 from research. And what are we doing tomorrow in class? Every student knows, they tell us. We always say that. You should be telling, the student should be telling the teacher what they need to do the next day. How do they know that? Because we need to figure out time of braking. So that's very natural. So you can guess what's going to happen next in the unit. I am going to hop back to, I got to pull up the agenda and I can't see it from, got it covered here. Because I think we're at the, oh no, we're going to do that. So I'll hand it back to Matt to do the time of braking, and then we're going to do a breakout room ourselves because there's a lot here. Okay, with that, you can tell, what do we need to do next? Of course, we're looking at the key. Students would just know we need to figure out time of braking. So with that, I'll hand it over to Matt for that.
Yeah, if you don't mind clicking on the tab to the far right. Yep. So this is done. First of all, we want to find our equation, our model for time of braking, and this is going to be done in Teacher Desmos. There's a template, and it starts off, like we tend to do, start simple and build to kind of complexity. Here they are finding a couple factors that might affect the time of braking, or that do not affect the time of braking, or that might significantly affect the time of braking. And so they are just matching those cards. And then we want to be able to interact. We have some reading, some interaction with graphs, and as well as some simulations that we do. So there's some reading on acceleration and speeding up and slowing down. Here's a new situation that they can decelerate in. How do we model that with on a graph? On the next slide, go ahead, Bradford. There is a simulation that kind of models this. What things might affect it? Well, of course, the velocity before shows how far it goes, and then changing the acceleration of the braking also will affect how far the car will travel. And so they play around with the velocity, the acceleration, and then that allows them to start to get a sense of the different things that affect it. Ultimately, they are comparing their data that they get to a graph and coming up with their best fit or their best solution for, on that next slide, playing around now with the same situations with the acceleration and velocity to see which of the possible models might affect or might fit for time of breaking. And so this is a bit of a multiple choice question where they're playing around with the different variables and seeing how that affects the time of breaking down at the bottom. And then the very last slide is really just for you as a teacher, and teacher Desmos, you can see if they got it. And so it allows them to really answer the question. And then what are we going to do? We're going to use that, put that into our system analysis, and code that into our spreadsheet later when we get to coding. So it's a way for us to, and Bradford shows it there. We would go and actually write that in on the paper, right in that location. Good. So yeah, I think with that, if you go back to the agenda, Bradford.
I think I closed it, but I'll bring it up.
Nice. Good. Yeah, so we're gonna have some just time for reflection. I know webinar is a fire hose, and we want some time to really get students or get you talking with each other and looking at that. So I don't have, could you put it in the chat? I have it somewhere.
Yeah.
But,
Yeah.
Good. And I need to, so Bradford just put it in the chat. And really we hope this time in the breakout room is just a time for you to discuss with other educators or from all over, how does the storyline help make sense of the physics that they are preparing, that they are learning, and prepare them for what comes next. If you don't mind, when you get into those breakout rooms, introduce yourselves. I have made breakout rooms of 4 or 5, and I am almost ready with them. Bradford, give me 1 second.
Yep, and we'll have that 5-minute timer. So at the end, we'll just close them, and yeah, and then also idea capture tool is a great place to put questions. We're going to hop over there and try to answer just a couple questions already up there. So that's really great.
Good.
Try to answer those while you're in there.
All right, great. I have that open. I will set a 5-minute timer on it, and we'll see you back here in a bit. I'm going to join room 11.
Okay.
Or no, room 12, sorry.
Okay.
Oh, no, we're good. I'm going to go ahead and pause the recording.
Yeah.
And hand it off to Bradford.
All right, excellent. And just like we do with students, what are we doing next? We go back to the system analysis. So you can see we've made a lot of progress. Really, all we have left is we got to figure out the mathematical model, the equation for distance a car goes while braking. Now that's complicated. We know that's the full kinematics equation. We know as teachers. So with students, again, this is another example. Start simple and build to complexity. It's a very easy shift for students. So what is the easiest acceleration? It's not something that has an initial velocity and slams on its brakes. The easiest acceleration is speeding up from rest, from 0. So we want to do that. We're going to do a ball, rolling a ball down a ramp, right? Classic alpha experiment. One of the first experiments to have a data table. So, all right. I'll say that actually we do hope to in the future change the supply list and eventually do this with fan carts. That is just to put that on your radar. Maybe that's a year or 2 away, but if you have, fan carts are a little bit expensive. But if that might take a couple years, so start planning ahead. It's a lot nicer with fan carts. But in any case, we are doing the simplest acceleration, and that is something speeding up from rest. The simplest is just you roll a ball down a ramp. So that's what we're going to do. So the distance to car while braking is a 2-step process. We're not going to get there exactly right away. All right. So, but the beautiful thing is, this is the lab template. I just want to say we are done with unit 1, and they now know in the hypothesis section, we now really want this graph, the hypothesis graph, to do some heavy lifting. And, every student knows that as the ball rolls longer, it will go farther. But they've already done this experiment, and they, ideally, and not every student always remembers this, but they should know. Some students will know that the slope or rate of change on this is the speed, and they know a ball speeds up. So depending on how much support you give, and I would say if you have a student who's struggling, walk over and talk with them and give them a lot of support. Okay, if in the first 5 seconds it rolls 5 and it's rolling down a ramp and speeding up, what's it going to do in the next 5 seconds? It's not going to roll another 5. They all know that it's going to roll farther. So, and I wish I had that slide open, but I don't. Maybe go back to the home page. I just want to see our 4 basic patterns. They know it's one of these patterns, right? Horizontal line. It's not a horizontal line. A ball rolls forward. It's not proportional. They know it's not rolling up the ramp. So you really can get, I think a lot of students without guidance will get to quadratic. With guidance, you could get almost every student hypothesizing quadratic. And that is an identity builder for them. If you quadratic, it's big and it's scary. Lots of students haven't done that even in math class. But if they're expecting quadratic, they don't know why. I'm not claiming they know all the details, but they know, hey, speeding up, that's maybe got to be quadratic. So that is there for you. And just know that if a class or you got students who feel really confused in class, doing a little bit of prep work at the beginning, a little bit of getting them talking about this can really set them in a good frame of mind to make sense of the data later. Okay, so that's just the peek we wanted to give there. We got the data tables, same as the ball on floor. So that's why we set up the ball on floor the way we did is, hey, this is basically the ball on floor lab, but except for we look at the ball while it's on the ramp. Okay, with that, I did make a picture. So there's that wild guess, and those are fun. So I hope, whoa. I'm trying to, it's off screen right there, and I'm trying to scroll over to it, but I lost it. Right here. It's on the right there. Maybe I'll just click and drag it. You want more than one ramp, right? They're going to take data on one ramp. So without making it too complicated, just duct tape 2 ramps together and just use a bunch of chairs to support it. We want the constant angle, and that's pretty good. We took data. And that's not perfectly straight, but that's straight enough that gave basically perfect data. So there's just 2 ramps together. Students don't see this, but I just want to show we're about to talk about the wild guess. We want to, you should measure how long it takes to roll down this ramp. And that is what you will do for your wild guess in your school setting. So there's other ways to do this. You can use just stairwell and other good stuff. I'm going to move that off screen. But anyways, measure how long it takes to go with whatever angle you set up for your classroom. That's what you'll ask them to wild guess for. So if that took 1.8 seconds, you would ask, hey, how far will this ball bearing roll? And you show a single ramp, and most students think it's going to be somewhere on the ramp. And then, of course, that's their wild guess, and we'll ultimately compare it to the data-informed prediction at the end of the lab. And again, only half the groups, you'll do 2 different ramp heights. And so only some student groups will have the data needed for the class prediction at the end there. All right, so there's a little peek there. There's a video of that too that just shows that. Okay. I'm going to get to make sure I'm hitting everything. So I'm going to pull up my notes on, let's say, it's obvious here, but here is just the card sort. It's so powerful. Most students get this set up, and these are not necessarily in order. So that's what this tells you. These are scrambled in case you have this and a student sees it. It doesn't give away the answer key. So in any case, it does go low, medium, high, and steepness, but these are all out of order. Okay, so with that, they of course put them in order. That's the card sort. And they just notice that, oh, the number gets bigger in the equation, and the upswing, you know, like just did this with IB physics. And, you know, a lot of them thought exponential. And so we need a word that's not exponential and it's not quadratic. Words that everyone understands, upswoopy. Some math teachers don't like that, but we've actually talked to a bunch of math teachers now, and they've come around. A lot of them are like, you're right. There's not a word that means that's ambiguous enough to mean, I don't know if it's quadratic or exponential. And we don't want students to say exponential when it's quadratic. So we need a more vague word. Upswoopy it's just so friendly. So many students get a kick out of saying it. But ultimately, we also want them to say the technical terminology, curvature. So as the curvature of the graph gets bigger and bigger, that every student can say that. And we want them saying it so many different ways, like 5. Lots of students will say it gets steeper, but actually all 3 curves get steeper. In fact, to be annoying, parabolas have all steepnesses from negative infinity, if we looked at the quadrant 2, to 0 to positive infinity. So it's a little bit sloppy to say this one gets steeper. It gets steeper faster. Love that. So we want them saying it 5 different ways. It gets steeper faster. It's more upswoopy. It gets a bigger slope faster. It curves up more, and it has a higher curvature. One other one that you'll hear is stretch. Math teachers sometimes talk about stretch, and that's super cool. Actually, if you're using Desmos allows you to stretch the screen now, so it works really well. That's for another Desmos and physics webinar, but you just can just see how stretch works. Anyway, stretch, curvature, upswoopy, it gets steeper, faster. Love that one, because that's also a great corollary to it gets higher velocity faster. So like that one. And we want them saying it lots of different ways. Okay, with that, I'll close that. And we hit the high points. I want to bring one last thing though. Okay, so card sort, and then
looking at the graphic
packet.
organizer.
So here's that packet again. Here's the graphic organizer. We talked a lot about these. You probably did a lot of them in unit 1. So that card sort's down here. All right, and then walk the triangle. Okay, in the mathematical model, it's a number because it's constant. Something about the ball rolling down a ramp. It's not its speed. It's not its distance. It's not its time. It is something else. But in the mathematical model, it appears as a number. In the graph, it appears as how quickly it gets steeper, faster, curvature, upswoopiness. In the real world, it's how quickly it speeds up, the rate that it speeds up. And of course, technical term, acceleration. All right, so that's the acceleration. And then just want to show you, here is a chance to, right from the data discussion, to get students ready for the conclusion writing. And we want to end on, why is this pattern quadratic, right? And we want every student to feel really good about that. Now, coming off of the Marble Lab, I'm gonna click out of here. I guess I closed it, but I'll stop screen share and spotlight. Okay, so remember from the Marble Lab, when we packed marbles, we knew that when you double the diameter, but we switched to a square now, that was tomatoes and circles was all to throw them off the scent, but then we want it to really be a good anchor. Some things, when you double the input, 2 things happen. It gets twice as wide and twice as tall. So the output quadruples. So we call that pattern quadratic. Why is acceleration quadratic? We just said some things in this world, when you double the input, the output oh my gosh, well, the output, sorry, totally messed that up. Some things in this world, when you double the input, two things happen. Why is time in acceleration twice? And with webinars, it's very hard to keep it interactive. So that fire hose, all right, two things. Time, okay, when we rolled a bowling ball on the ground, give it twice the time, it goes twice as far because it has twice the time to roll. Time on a ramp does two things. Time gives it more time to roll, and it gives it more time to speed up. So what are the two things acceleration does? Why is it quadratic? Why is it 1/2 AT squared? Oh, sorry. Yeah, good. Why is it A times, times, time? That's a bad one. Times multiplied by time a second. Oh my gosh, that's all of those iterations sound horrible. Sorry about that. Distance equals 1/2 acceleration multiplied by time, multiplied by time. Time is in there twice because one time is allowing the bowl to roll longer down the ramp. The other time is in there because it's giving it time to speed up. All right, so if you're willing, actually, I don't know. So this is that time. We want students to not only learn the equation, we want them all feeling good why it's quadratic. And that is the power of patterns, is that almost all students feel pretty good about it being quadratic. And so they will write that in their system analysis. So I'll go back. Matt, if you turn off the spotlight, I'll go back to the screen, although I closed it. But maybe I'll quick from history, bring it back up. Get there. All right, we actually really do want explain why acceleration is quadratic, and said it a couple times there. So that is pretty good. Okay, now I did kind of slip in the 1/2, and just want to say it explicitly. Back when we were willing to spend weeks on this unit, yes, we created arcs where you can have students discover that the C value is not actually acceleration. It turns out to be 1/2 the acceleration. And we don't think that's worth the time. You can have them discover that constant is 1/2 the acceleration, or you can have them discover how electric guitars work. And I'll just say, in the moment, sometimes many physics teachers really want students to understand that it's 1/2 acceleration, and they'll take a whole day for it. But come spring, most teachers wish they had that one day back to spend more on electric guitars and climate change. So really strongly recommend, just tell them, save something for senior physics, AP physics. They can go and discover and do area under the triangle, all that good stuff. For us, really, there's something along this line. I'm not saying do this derivation in front of teachers, but somewhere along the line, you just explain, and I keep it in small group. It's not even a whole class. Just as every student gets that the constant is acceleration in the packet, they fill that out. And then I say, just take the scenario that's 1 second long. And let's just say you're dropping something. So the acceleration is 10. It's just a nice, easy number with gravity being so close to 10. If you drop a ball for 1 second and the acceleration is 10 and the time is 1 second, most students who don't realize it's 1/2 would say, oh, it has to go 10, but that's not fair, right? If it speeds up to 10, it wasn't going 10 for that whole second. It started at 0 and it eventually at the end goes up to 10. So what should we actually do? We should actually use its average velocity. And of course, if you go from 0 up to 10, on average, you were going 5. And that does actually make sense. So it's half the acceleration, because as you speed up, it's not fair to use your end velocity. You should technically use your average, which is really just the beginning plus the end divided by 2. And again, this is hand wavy. I just want to own that. I'm not saying that I'm trying to have every student do this calculation. We are basically saying tell them, but I don't mean literally tell them like C is 1/2 and say no more. but you can walk them through, and that's what I mean by hand wavy. Most students feel pretty good about that, and we move on. And we have IB physics. In IB physics, you will derive that a couple different ways, actually, or AP physics, or whatever's higher level junior, senior physics class you have. Save that for them. Hand wavy, you'll want that day back, but I don't know if it is the right fit. Your students the best. There is 2 options to take some data and then look, in fact, at the velocity versus time graph and see that the acceleration turns out to be half the number you get when you graph the distance versus time. So that's an option there for you, but just want to make it super clear. It's in the unit 2. I did highlight it there for a split second. That narrative, those are worth reading, or I hope they are. And if they're not, give us feedback. Sorry, where am I? Right here. So we're in the constant acceleration, and right here it's saying, hey, you'll want that day back. That's the recommendation, but your classroom best. All right, so that pretty much wraps up. We've gotten the simple model of acceleration. That's the simplest, speeding up from rest. I'm gonna do one last check of my notes, and then I'll hand it over to Matt. Or actually, I'll just, maybe Matt, you're already looking at, so I got too many tabs open. So anything I missed, Matt, and then take us to the next step.
Sorry, muted again. This is just a good looking at the acceleration, we're halfway there. We're actually not quite to looking at we did the simpler model starting from rest and speeding up. So we really do need to have a conversation, an activity around finding that mathematical model for constant acceleration while we are slowing down. And so students would, we would put up our poster. We have constant acceleration there. We would make our prediction. We'd go back to rolling that ball on the ramp and allow them to make their prediction. We would put a T in this. Yeah, you can see Phys 5 of how does we ask a question, we take some measurements and find a pattern to predict the future. So we really do want to wrap that up, but then take that and start to look at how can we apply this to our texting and driving situation. We have our math model for constant acceleration, speeding in the form of speeding up, but what happens once we have initial velocity that's left? And so we will look at an activity, and we have a spreadsheet that we're going to do that with. And Bradford, do you mind running through the velocity?
Yes. Excellent. So just want to show how light of a touch this is. So there's a whole backstory in the video where they actually watch a little clip of Mythbusters, and don't want to overdo it. I really want to show how light of a touch it is. It's surprising how light. So we just literally give them this. This is the student version. And this is about a scenario with a bus. There's someone on the sidewalk. Grant is watching from the sidewalk. Okay, Tori is, actually, is that right? Yeah, Mythbusters, Tori and Grant watch from the sidewalk. So Tori is on the sidewalk watching. The bus is going 60, and these are not realistic numbers. They're just super friendly. That we picked unrealistic numbers, but they're super friendly. All right, so the bus is going 60 meters per second, because 60 miles per hour. It's just easy numbers. That's really too fast. Maybe that one should be changed. Okay, but it's 60. It's so easy. And then there is a Frisbee being held and accelerated inside the bus, or the ramp lab. You could put the ramp lab there. And yep. And eventually in the future, one day we'll be able to say fan cart. The fan cart is accelerating in the bus. But anyways, it's a Frisbee for right now. So there it is. Velocity of the Frisbee is being accelerated. 0, 10, 20, 30, 40, 50. Yep. And then, hey, there was a little mini lesson about relative velocity. Really, I mean, mini as in 5 minutes long. And all students, pretty much no one has trouble with this. Hey, if the bus is going 60 and the Frisbee's going 10 inside the bus, the person on the sidewalk will see it go 70. And let's just click on this cell. How did the computer know? The computer doesn't know to add the velocity. So click, and hey, the computer, we wrote equal sign B5 plus C5. Oh, the computer just took what was in this cell and added what was in this cell, and that equals 70. Okay, now lots of times coders need to put stuff for humans to understand. So let's look at what the coder did. The coder told us the velocity of the bus is equal to B, and that was 60. The acceleration is the velocity inside the bus is changing because it's accelerating, AT. That is what we got from the lab that we just did in terms of velocity. And so if you're accelerating by 10 each second, 1 second, oh, we can even take a peek. What does this do? Oh, this is equal to 10 times A5. Oh, A5 is over here. That's the time. Okay, good. Just to show the light touch, quick, just make a copy of it. The light touch, all students have to do is, oh, there's a question mark here. They need to enter. What did we do? Well, the computer just added these two together. To tell humans what this was doing, they just need to delete the question mark and put in. And they all do this without, that totally makes sense. What's the velocity going to be seen from the sidewalk? The bus plus the velocity inside the bus. It's just a no big deal. It's that simple. And we start with velocity because that's that simple. Then we go to distance. It's equally as simple for the most part, except for the equation has 1/2 AT squared. But as awful as that normally is for students coming off of the ramp lab, most students are like, that's not that big of a deal. Just because some teachers don't see this, do want to have you read this. There is a great graphic, Desmos, Matt coded, so helpful. So here, this is just bonus material, just another little visual to help students. Lots of times they still get it without this, but it's so nice to show. All right, here is the constant velocity of the bus. If we want to turn the Frisbee on, I want to go to, let's look at the Frisbee inside the bus. There's that constant acceleration. And that's that nice parent function quadratic, 1/2 AT squared. All right, now what will someone see? This is what you see inside the bus. Of course, the whole bus is moving. So what does someone see on the sidewalk? Both of these at the same time. So we can turn off passenger view and be sidewalk view. And so it accelerates inside the bus and the bus is moving forward. So it's both of those at the same time. So let's go back here. Again, we could check the code and yep, it's all that good stuff. We could check this code. Oh yeah, they programmed 1/2 AT squared. Anyways, to keep it focused, this is like a couple minutes on it. What's the distance that the Frisbee goes? It's how far the bus went plus 1/2 AT squared. And there we go. That is the derivation, or not even derivation, but that's the reasoning. And students now have the kinematics equation. The total distance an object goes is the combination. It is the velocity times time plus 1/2 AT squared. And so that's our prize. We now actually have the mathematical model for any constant acceleration movement. And so we will program that in, or we'll write it down on our packet. And then of course, the next step is going to be coding the spreadsheet. So the distance while braking is initial velocity times time plus 1/2 AT squared. Okay. And so now we got our system analysis done. We're ready. And I'll pop over to, I gotta keep checking my notes because there's just so many things to try to say a multi-week unit this quick. Want to do a quick check, do a quick in check with Matt.
So,
but look, go ahead, go for it.
Yeah, so we have the system analysis skin, and we just wanted to kind of highlight that this is another time that we would do stronger and clearer. We have a slide there. So up above, actually, could you go back one slide, Bradford? Just
Yep.
like, yeah. So we have our system analysis complete. We are ready to move on, but we want them to, process and take some time. So stronger and clearer, again, we would go out in the hall. And this is it's so fun, especially to hear when like other classes are doing it, and all of a sudden there's just a burst of 15 conversations that are happening in the hall. So it's just a nice way to solidify all those things that we've done. So once we have that, we are really ready for coding our spreadsheet, our app, to make our predictions. And of course, we have lots of support for that. So, Bradford, if you want to scroll down.
Yeah. Can I do one? Let me toggle
Yeah.
one time. So here,
Yeah.
I'm going to toggle to the answer key, and then we'll back off and look at the very. So here is our, this is sort of the mostly completed system analysis. And then let's take a peek. I can close, all right, I'll leave that open. Here's the key for the simulation. You can just see how visually the same it is. Okay. So with that said, I'll say level 0, and I'm going to hand it off to you, Matt. Level 0, which is too much for most people, is a completely blank spreadsheet. That, if that's the right fit for your students, that's a challenge, but many students are successful at this. If this is your first year, that's probably not a good fit. You know, it is the scaffolding level 1, 2, and 3. They're all good experiences, and students do get a kick out of making that. We actually learned this. Students taught us this. And now that it's so good, we want most students to see that on their coding because it matches their system analysis. So that's a nice touch. But you know what? If you're kind of running behind, is teaching students to make this cool image in spreadsheets, is that more important than climate change? Probably not. So if you feel like, you got to think all the way to the end of the year, that's a great thing for students to do. It is really a nice touch, but with that, I'll throw it on the mat to show how you can choose the right level of time and what they're spending their time on by choosing the levels of support. So I'll get there and let you say that.
And Bradford, could you zoom in really
Yep.
far? And I don't think it's worth showing all of them, but maybe we could show one. So you can see all of the supports there. This is in the teacher calendar under the section where we are actually starting to think about complex motion and thinking there. So maybe click on, just going from level 0 to click on level 3, just to show you, just to show an example. Here is like a spreadsheet that is essentially all set up in terms of format, in terms of the formatting, but not set up in terms of the coding. So this is jumping forward, and throughout, we would be highlighting in our paper system analysis, what are the inputs, what are the outputs, what are those needed calculations. And so in their system analysis, they have a living document that they can now use to be able to code each of those. And you can see those highlighted there with each of those sections there. So that's just like, choose the level of support that your students need, and always taking into consideration, the timing of how long it takes. But there are those supports there to help get that. And of course, I don't know if I'm getting ahead of myself, but back on the teacher calendar there, Bradford, I don't think we'll show them, but there are video tutorials, of course, to set up those spreadsheets. So each of them are videos.
This is a real B&H.
Oh, yeah.
That's
That's an advertisement. So yeah, we'll get.
yes.
Oh, it's worth saying.
Working, yeah.
Yeah, everything will be a safe link, actually, in maybe a month. So safe links is a subscription paid for, but that'll strip all the advertisements off of any video clip we have in Patterns Physics. So that is happening as we speak.
Actively working on it. So yeah, so each of those are different tutorials that help look and help students code. And so we moved to that model of, we used to in front of the class code in A2. Now we let our students use their system analysis and use tutorials if they need them to be able to do that coding there. So those are all the supports that are there for allowing students to be successful with that coding. With that, I think we're going to really start to look at building complexity, look at some student examples, and see if we can handle taking on all those situations that we put at the start. So yeah,
So let's go to just for fun, and I lost it in the chat, but I'll try to remember. So here's one, an alert driver. Let's just go to that baseline. We had that 10 meters per second. Let's say your groups of students said the typical time of distraction was 3.1. Of course, we just velocity times time, get 31. The reaction time, and 9. And it's worth saying right away, what do you notice about this? Some students, sometimes teachers have reported, and I've had it happen too, like students think like, oh, but I'm really quick with my reactions. Okay, fine. Let's just say instead of 0.9, you're only 0.5. What is the real problem with texting and driving? It's the distance that you're before. It doesn't matter your reaction. Your reaction is not the most key one. Now, whether 3.1 is realistic, yeah, actually, there's definitely cases where there's so many students find videos of people videoing other people texting and driving. And so, we've had groups watch the video and time people on video. Blah, blah, blah. But anyways, we've now discouraged that. So there's just a lot of garbage on YouTube on those videos. So, okay, any case, but that is just right there, right in front of you. Okay, so it's so cool though. Start simple, build to complexity by not worrying about the exact breaks. Now, is this one worthless? Is this pointless? Or if it is icy roads, let's do that one quick. Icy roads. We did not create this model with icy roads in mind. Is this worthless, or can we change it? And I strongly suggest if you go down here, let's duplicate this. And then we would rewrite this. This would be on icy roads. And we got to iterate this. So what would change? And I'm willing to try to take it from the chat. What would change the velocity? You are still going 10. You might still be distracted as long. What would change if you're on icy roads? Can we modify this? Distance braking, and specifically what would happen on an icy road? Your brakes would go down. And what would they go down to? I'm not too worried about that, but we just know that it would go from like -8, and you got to think about that. Icy roads, negative numbers, but -8, and that would probably go to, I don't know, -4, -2. The point is, we just want to show them rapid iteration. Let's say -2, and watch for it because you'll see the screen. I'll hit enter, and it recalculates quickly. And actually, again, we said coders do things for humans. Deceleration of braking on ice. We want to make sure that they don't forget and come back to this and just think -2 for all cars. So we change it, distance while braking on ice, and it's -2, and they see that happen. So that's really good. There's that if statement down here that car went 61 and the person was 33, call 911. Let's say the person was 100 away. Oh, that changes it. Students love that. They do that if statement. And we did that back on day 1. Yes. So they do that little conditional if statement right up here. You can see it. It's probably kind of small, but okay. There was some other examples and I've forgotten, and with the fire hose of the webinar, what's another one? It is on students always love to talk about someone who is intoxicated. That one gets a little bit harder, but if you were intoxicated, I'm being annoying and I don't want to be, but I want to be a little bit like, is this worthless? Do we have to just throw this away and start over from scratch? Or can we modify? What would we need to modify if the driver was intoxicated? You could even yes, reaction time for sure. So time of reaction while intoxicated. And what do you think that is? You know, again, the point is not to get the exact right number. We want to show them by starting simple. Now we have a model, a simulation. Actually, I want to pause and say that one more time. We've created a simulation. This is not a 3D goggle simulation, but this is a simulation. And how cool is it? We coded this with equations they got from experiments that they did. So they coded a simulation with experiments that they got from the ball on floor experiment, the ball on ramp experiment, and then combined with some computational thinking. Okay, while intoxicated, this might go up to 1.5 or even more. And you might even argue that time of distraction, lots of times students would say, if you're intoxicated, you might end up just not being as thoughtful and being distracted longer. So it might go from 3.1 to 4.5. And again, so all of a sudden we can quickly iterate. And doing the time check, we do have time, and I closed the slides, but there's one slide that really like to show often because it's student generated, and it's also another one that lots of times students are like, what? Yes, we can iterate to handle even that. So if I go down to it quickly, there's that
159.
Mythbusters. What? Yeah, thank you. You said it, but I missed it. Say it one more time.
159.
159. Thank you. Okay, here is a student generated video. Again, you know, so often with public service announcements, it's always that like shock factor that has it again. Yeah. Excellent. And again, big theme of this unit is we can look at these and think STEM to enhance the discussion. Okay, so let's go back to our, you drift into oncoming traffic. Oh my gosh, we set this up for a car and a pedestrian. Is this worthless? Do we have to throw this away, or can we modify this? This one's a little bit more challenging, and I think in the webinar might, okay, so it's now not, oh, this one already is modified. I somehow grabbed one that was. Yes, the velocity of the two vehicles approaching each other. It's the two vehicles approaching each other. And so if the car was going 10 and the truck was going 10, remember the relative velocity, what would someone on the sidewalk see them approach each other? 20 meters per second. Everything gets recalculated. So that's nice. The velocity of the two vehicles. So we ask students to, at the beginning, to trust us a little bit, start simple and build to complexity. But now the proof is in the pudding. They see now that we started simple and didn't try to take on night and old brake pads or a super heavy car that couldn't slow down very much. We now see that we can iterate to handle more complex situations. All right, so we're about to bring it home, but there's a lot of good stuff I hope you see happening here. We've taught them the power of computational thinking with spreadsheets and shown how it allows the human brain plus a computer to go through a bunch of situations quickly, start simple, build to complexity, has really lived out. They can see how starting simple, and now that we want to handle more complex situations, we can do that. All right, so we're about to show you some resources to have students see the value in it, and then ultimately ask that question from the health teacher is what brings STEM to the social discussion around texting and driving. Okay, with that, I'll pause there and hand it off to Matt to see any things that I've missed.
Yeah, so thanks. Actually, could you click on just 3 tabs over your 2CT key to the right,
Yeah.
Thanks. Yeah, so just wanted to show, like, here's a student generated app that they made. So this allows for some creativity, allows them to kind of move around. So this is one that a student made that they used to, do their prediction. It was all working at one time, and they are able to kind of reformat, reuse, make their texting and driving simulator. On the next tab over, Bradford, we want to leverage their engagement and ownership in using their own evidence from the simulation that they coded themselves to elevate their own claim evidence reasoning writing. So in this, this is a potential assessment if you choose to give it this way, where if you don't mind zooming in down at the bottom, right there, Bradford. They are looking at an argument of why texting and driving is potentially hazardous given a certain parameters at the start: distraction time, reaction time, and they're able to use how far did this car travel, and use their spreadsheet for that information. So they can see their evidence there, they're quoting their referencing their spreadsheet for the reaction time. They're referencing their simulation. How cool is it that they are coming up with evidence from their simulation that they made? There, they can you can see that they're talking about how far the obstacle will be away as they're looking, and then they change the parameters and compare how does a person who's texting and driving compared to somebody who's alert and driving, and compare the total distances, the different distances that the cars travel along the way. Later on, as Bradford was mentioning, that simulation that they made is good for other things as well, not just the texting and driving situation. And so there are opportunities to have students look at a different situation. So in this case, they chose drunk texting versus sober alert driving. And so, of course, using that spreadsheet, modifying that spreadsheet in a way to modify somebody who is intoxicated, by changing their reaction time, and then being able to compare with evidence from their spreadsheet the differences between the two. So it really gives ownership. It gives ownership of, completes that circle that we made that from the beginning, from the health class, and then we come back to it at the end and actually use it to inform our decisions. So with that, that's a good arc of the texting and driving unit, and I'll hand it back to Bradford to summarize, and then we can look at our breakout.
Yes. Okay, excellent. So actually, that is really all of it. The one thing that we didn't show was the supports in the packet. So just some of the big ideas around all of that motion, just a chance for practice, and then that computational thinking with their app. This just, it walks them through some of the typical ones, what happens with old bad brakes, drifting into the oncoming traffic that we saw in that one. And then they come up with a new scenario. So that's getting them all ready for that final arguing from evidence. Oh, and I closed it. Okay, I'll quick bring it back. One other thing that is a great thing to point out, Zoom, is we also just asked them, how the last couple questions are, what's the outcomes of using STEM in a social discussion around texting and driving? And there's some other public service announcement videos. in the one, and some are more humorous than others and good. But in any case, like these are definitely cherry picked examples, but the trend is really there that students say like, oh, it was actually nice to actually hear some numbers instead of just that typical everyone's happy in the car and they're having a good time and then wham, broken glass and all that stuff. So there's that. And then it's also this question, how did you use the tools or the mindset of a scientist, an engineer to assess the ones? And that's something that we always hope for with students, that they're metacognitive or that they spend some time thinking about that, but we often don't ask them to write about it. So in any case, this has been one that we have just routinely again and again. It is chicken soup for the science teacher. It's really nice to hear what students are thinking, and being asked that gets them to think about that. So some students haven't thought about it. Some, you'll see from their responses, they really are seeing how, oh wow, I'm getting the mindset. Like I can look at the world, I can take data, I can think about it. And not, I was going to say in a mathematic way, but nothing like math class, right? This is very different than most traditional math classes, but they really start to see how you can use numbers and take data to get a more data informed prediction. So, and then overall question. So there's that as well. Okay, so that was a lot in the fire hose. That we need to check the idea capture tool for questions, but did want to just give that last think, pair, share, and maybe we'll keep it short, just maybe like 4 minutes, but just to go in, it's just a nice way to end, get a chance for reflection. We'll get questions answered in the idea capture tool and bring it back to just close up the webinar.
Good. So I just put the question in the chat. Just choose one of the following. I can't imagine that everyone will share out, but we also want to honor people's time. So I'm going to just set a 4-minute timer. Every group's the same, except for 2 groups had to get merged because people had left. So we will see you back here in 4 minutes. If you don't mind just reflecting on one of those 3 things: starting simple, building to complexity, coding to learning, or students generating on evidence in their own CER. So I'll open those up. We'll see you back here in 4 minutes. Let's see. Good.
Do we want to pause the recording?